induction states that whenever there is a change in magnetic flux, is very important. Whenever there is a change in magnetic flux, an electric current is induced in a closed circuit or an EMF is established in the closed circuit. So that was the basically given by the Faraday's law of electromagnetic induction. So this clearly states that rate of change of flux induces an EMF. That is the meaning of the Faraday's law of electromagnetic induction. So the statement here you can see E is the EMF. So or also you can say the voltage is minus of d phi b. Phi b is the magnetic flux. So d by dt of phi b. So this gives you the first statement of this, the first statement of this the Faraday's law of EMI. Then we have also seen that what could be the possible ways by which we can change the magnetic flux. So flux was basically, what is the flux? Flux is basically integral of B dot ds. Yes or no?
Yes, sir.
Yes. So either so B dot ds means B ds cos of theta. So as I had shown the last slide yesterday, that either you change the orientation or you change the area. As you can see, this is a small area, this is a large area, or you change the magnetic field, intensity of magnetic field. This is a uh, means thin arrow and this is a thick arrow. So thick arrow means more is the magnetic intensity of the magnetic field. So either by these three ways we can induce the EMF in a circuit, right?
Yes, sir.
So this we will see with the proceed. So as you can see, a uniform but a time varying magnetic field. See, this is very very important. Time varying. This, what is the meaning of the time varying magnetic field? That this field is induced. This field has been created by passing the time varying current. And what is the time varying current? Which current is the time varying current? Hello?
Means AC.
Sorry?
AC.
AC, exactly. AC, the alternating current is the time varying current. So the time varying current, whenever you is creating a magnetic field, that field is time varying magnetic field. So whenever you are passing that time varying magnetic field through a circular coil whose normal is parallel to the magnetic field, coil's area is given, its resistance is 1 milliohm. So B varies with time as shown in the graph. As you can see, B is varying with respect to time. As it is increasing, then here it remains constant, then again it is decreasing. So you have to plot the current in the coil as a function of time. So this question is having some importance. That's why we may discuss it. E is equal to, we know that by Faraday's law, minus of d by dt of flux. And what is the flux? B into A. Again, A is constant, so we can take it outside and we are with the dB upon dt. Yes or no? Then we know that by the Ohm's law, voltage is equal to current into resistance. Yes or no? Speak a little bit louder. Your voice.
Yes, sir.
Yes. So I is equal to E upon R. So E from this expression we can put here, and then we get I as minus of A upon R, which is a constant quantity, times dB upon dt. Okay.
Yes, sir.
Now how to plot this? You see, when t is between 0 to 3, so dB upon dt is change in the magnetic field on the y-axis by change in the time axis, right?
Yes, sir.
So this is simply 0.1 because from here to here it is 0.1 and here to here it is 3. So 0.1 upon 3, yes,
Yes, sir.
this is minus of 0.33 ampere for this one. Then for the next For the t lying between 3 to 5, of course, its slope is 0 because this is constant.
Mm.
Ye-
Mm.
Yes. And then after that, the slope is decreasing. So we can find the delta b upon delta t. So from delta b is again 0.1 because from here to here it is coming down 0.1 in the next 6 seconds. So this will be positive of 0.167 ampere. Of course, because slope is negative, but one negative is already there. So that's why it has become positive. Yes or no?
Yes, sir.
So its current will be like this, starting from 0, it is coming to minus 0.333, then this remains, slope is 0 means this remains constant, then again it is increasing, then again constant, so like this it will go on.
Mm.
Clear?
Yes, sir.
So Lenz law, already I had told you that this opposes the change in the flux.
Mm.
This already I have said that this opposes the change in the flux. So
Mm.
see, there can be a very concept that why it is opposing the change of the flux. So this is with respect to law of conservation of energy. There can be a question that Lenz's law is related to law of conservation of energy or not. Yes, it is related to law of conservation of energy. You see, a very small statement is there. If Lenz's law were not true, suppose somebody says no, it will not oppose the cause, rather it will support the cause. Then,
Mm.
if there were a positive sign in the Faraday law, then a change in magnetic field would produce a current which would further increase the magnetic field. You see, this is very, very important. If suppose somebody says that why negative, I don't agree with the negative, then okay, you take positive, but see the consequence. And then later on, you will conclude that it is contradicting the very fundamental law, which is the law of conservation of energy. How? That I will explain. Here it is there, just I will explain. So till now it is clear what I am trying to convey.
Yes, sir.
Yes. So it is saying that which would further increase the magnetic field. So further, and
Mm.
once the magnetic field will increase, we know that by the Biot-Savart's law there is a relation between field and current. So more is the magnetic field, more will be the current. Yes or no?
Yes, sir.
So it will go on increasing and increasing, and the current will go on increasing and increasing. So this cannot be possible. That without any external supply of energy, the energy will go on increasing and increasing. Okay.
Mm. Mm.
So this will violate the law of conservation of energy. So, to obey the law of conservation of energy, the current should be in such a direction that it should oppose the cause. And once again, I am repeating, what is the cause? Cause is either the change in, either the increase in magnetic flux or decrease in magnetic flux. That is actually the cause. So we have to look the problem wise and example wise. We will have to be careful and we will have to look that this current is induced in the circuit either or either by increase in flux or by decrease in flux. Whether increase in flux has led to the induction or decrease in flux has led to the induction. If increase in flux has led to the induction, then current should be in such a manner that it should decrease the flux. If decrease in flux has led to the induced EMF, then it should be in such a direction that it should increase the flux. Are you getting
Mm.
my point?
Yes, sir.
Yes. So, if any doubt, you ask. Otherwise, see, let us practice with the Lenz law. First one. In which direction is the current induced in the coil for each situation shown? The N magnetic pole moving towards the coil from the above page. Can you try it, please?
Mm.
Magnetic pole moving towards the coil from above the page. Any idea?
Anti-clockwise.
Sorry?
Anti-clockwise
Anti-clockwise, are you guessing or do you have applied some concept?
means
Means have you applied the Lenz's
I
law
told now.
or just you are guessing? Counterclockwise, anti-clockwise is the right answer. But thing is that have you
Okay.
understood? Can you explain it? Or just arbitrarily you are saying?
No, sir, you have already told this. Means not this slide before. Means not magnetic pole is coming towards it. Means
Sorry. Speak a bit louder.
not means north pole is coming towards the coil.
Yes.
Then it will oppose the course means there should be also north pole.
Yes. Then only it would be repelling the North Pole. So yes.
Then anti-clockwise current.
Okay. Good. Very good. So here, as you see, the next part, the North Pole being the pole moving towards the coil in the plane of the page. So in that case, it was the above the page. Now it is moving in the plane of the
Mm,
page, like this. So
mm,
now, what would be the answer? Hmm?
mm,
Think of it. Little bit. Try to think of
mm,
it. Here actually, one class I will take one day. I will like, keep some more slides whether this how to
mm,
this north and south is being designated in a wire. That concept actually we have missed. So here it will be the thing is that as it is the north moving towards this. So you see,
mm,
as in the plane of the paper, and the answer is very specific, no current. So means why it is saying no current? Can you try to answer? Because see why it is saying no current, because there is no change in flux. See, in the plane of the paper, so what is the angle between this means area and the field?
mm.
See, this is like this, try to understand. This is like this is going, and the normal to the plane is the like this, so angle is of course 90 degree.
90 degree.
Yes or no?
Yes, sir.
So BA cos theta cos 90 would be
Yeah.
0. So we need to be this little bit. These things are a little bit complex. So we need to be a little bit more. Means we should go for the little bit more practice and little bit more careful. Some more are there. See, this what does this encircled dots represent?
Means
This encircled
magnetic
dots.
field
What do they represent?
into the page,
Sorry,
into the page uh,
no. This encircled dots. What do they represent?
means,
That is magnetic field
magnetic field
is out of the plane.
outward out of the plane.
Now see, this is coming away from here. So right out of the magnetic field that points out of the page. So now see that from here you can very easily understand what actually Lenz law is. This is a good one. See, as it is coming out, so means
Hmm.
flux will decrease or increase.
Flux will decrease.
Exactly, flux will decrease. Then it is saying that current should flow in such a direction that it will oppose the cause. Means current should
Hmm.
flow in a direction so that it should increase the flux. Yes or no?
Yes.
Yes. Now to increase the flux means
Yes.
field should increase. Yes or no?
What?
It is saying that you said that flux
Ah.
is decreasing. So Lenz,
Ah.
Lenz said that now the current should be in such a direction that flux should increase.
Ah.
Up till here it is clear.
Yes, sir.
So it means that to increase the flux, the strength of magnetic field should be enhanced. Yes or no?
Yes, yes.
So it will be enhanced only when the magnetic field produced due to the current should be also outward. Then only this two will be added, and the magnetic field will enhanced. Yes or no?
Okay. Uh,
So now you tell me what should be the direction of current. This we have studied in the magnetostats, that if this is a circular loop, in what
uh,
direction the current should flow so that the magnetic field will be outward. It's very simple. Forgotten? Remember? No.
Anti-clockwise?
Anti-clockwise.
Clockwise. Current should be.
Counterclockwise is the answer. Are you confident enough that you have done it, or shall I explain a little bit more?
Outward means
Shall I explain a little bit more, or uh, you are confident enough?
not
Yes?
direction.
Tell me. Are you confident enough?
Not
Or the
no, sir.
no? So, no issue. I will explain. Just actually, I'm looking that better if I can show you on my. If I can switch on my video, that would be better. See, yeah, can you see me?
Yes, sir.
So if you remember about a circular group, I told you that same right hand thumb rule, that the
Mm,
this curling fingers show the
mm.
direction of current, and the thumb shows the field. Do you remember?
Yes, sir.
Yes. So that's same. Now now the using the Lenz law, we know that the field should be outward, means thumb should
Mm.
point outward. This is known. So how the finger should move? This should, you can see,
Mm.
this should move
Oh,
like
yes.
this. So of course this should be
Uh,
anti-clockwise. Yes or no?
uh. Yes, sir.
So now we are doing the reverse. Now current direction we are finding and field direction is
Mm.
known. Previously,
Ah.
while we were in the means previous chapter, the magnetostads, their current direction was known, and we were deciding the field by the Biot-Savart's
Mm.
law. But now
Mm.
opposite is happening. By the Lenz law,
Okay.
first we are deciding what should be the field. Either it should be downward or upward. How to decide the downward or upward is that whether the means it should be enhancing the flux or diminishing the flux. Accordingly, it should be
Okay.
decided.
Mm.
Now, I hope it is a little bit more clear. Yes or no? You see the
Yes,
thumb.
sir.
So no issues. Just a minute. Yeah. So here we were there. So I hope the screen is visible to you.
Yes, sir.
Yes. So another one you may try shrinking the coil in a magnetic field pointing into the page. What should happen?
Means shrinking means area
Try.
will decrease.
Yeah, try at least.
Area will decrease. Magnetic flux will decrease.
Okay.
Then it should increase current should be in such a way that it should increase magnetic flux.
Exactly, by the Lenge's law. Very good. Then
Mm, then
you have already reached to the answer. Then the magnetic field should be in such a manner that it should be, sorry, the current should be in such a manner that it should be into the plane of the paper. Yes or no?
okay. Yes, sir.
Yes. So now you apply that right on thumb rule.
Okay. Mm.
So it will be clockwise. Of course, for the
Yes, sir.
upward it for the upward it was anti-clockwise. So for inward it will be clockwise. Yes or no?
Yes, sir.
Yes. Now it's becoming clear.
Yes, sir.
Yeah. So likewise. Okay. So now I hope that Lenz law is clear at least. At least.
Yes, sir.
Okay. So this is what the minus times n d phi by dt it was explained. So here actually this equation is now combination of both. Now we can say that Faraday law is giving the magnitude of EMF and this negative sign is deciding the direction of EMF.
Mm.
Yes or no?
Yes, sir.
Yes. So this statement is combination of Lenz law and the Faraday's law. Okay.
Okay.
Then there is a term motional EMF. Now let us see. The questions have been asked in the GET also, and this is also important also. So what is this motional EMF? You will see very quickly. We know that the EMF is minus of d phi b by upon dt, right?
Yes, sir.
Now a conducting loop is rotating in a magnetic field. As you can see in the figure B, these are the magnetic field lines. This is a field. This is a conductor placed in this field at some angle theta. Okay.
Mm. Mm.
So now when it is rotating, so according to the rotational motion, this will be see D, if suppose the magnetic field is given like something like B is equal to B naught sine of omega t, right?
Yeah.
So here it has not been derived, but I am saying that see, if phi B is what? B into A,
Mm.
let me write here, it will become more clear. I think you are having some confusion. Suppose B is equal to B naught cosine of omega t. Because it is time
Mm.
varying, na? So B is equal to B
Yes.
naught cosine of omega t, right?
Yes.
So what is the phi? Phi is B times A. What is phi
Ah.
B?
Mm.
Phi B is B times A, yes or no?
Yes. Yes, sir.
So we put here at the E, so E will be, and suppose this is for the n number of turns is there. So this will be multiplied by n, yes or no?
Yes, sir.
So if you put this here, that d phi B by dt, so B naught cos omega t. So what is the differentiation of cos omega t?
Sin omega t into omega.
Yeah, so minus sin omega t into omega.
Oh, into omega.
That is what here it is written. NBA omega times sin omega t.
Mm.
And E is equal to IR, yes or no?
Yeah. Yes, sir.
So just I will be this divided by R.
Yes.
Okay.
Yes, sir.
Yes. Any doubt?
No, sir.
No. So see, so power is what? Voltage into current.
Yes.
If you multiply this two, if you multiply this E into I, what will be the answer? Or just you multiply E with the I. So E is this much. You multiply with the I. So this will be BINA. Bina. This is just a word we used to remember. Bina omega sin omega t. Yes or no?
Yes.
Yeah. So this is what. So see, wait. Motional EMF is still due. What we are trying to see. Now see the motional EMF. What actually it is saying. Now see, this is a coil. This is being dragged. See, this portion you see. This is being dragged in this magnetic field, as you can see, with a velocity v. This you see, this
Mm.
I just suppose we have put a hinge, and putting this hinge we can pull it back as it is shown with a velocity v.
Mm.
Are you getting the point?
Yes, sir.
Yeah. So then what will happen? Equation remains same. E is equal to minus of d phi v by dt. Yes.
Yes, sir.
Do you remember this equation? Magnetic force. This I
Mm.
told you Bill sine theta.
Yes, sir.
IL cross B.
Mm.
Yes or no?
Yes, sir.
Yes. Then what would be the mod of E? This actually has not been derived, but if you use this, then you will be getting a very popular equation that EMF is equal to BLB. This is a very, very popular equation, and this is known as motional EMF. Why we are calling it as a motional EMF? Because this EMF is induced only when this conductor is in motion. If this V goes to 0, then this E goes to 0.
Mm.
Are you getting the point?
Yes, sir.
And it is very easy to understand how this has been derived from here. If you see d phi b upon dt. So you see x is the variation here. Then you will get a term here, means b is constant. Fine, as you can see here, b is constant. Uh,
Mm.
the area, sorry, the L is the length of this, and there is a displacement along this. The x is changing with respect to time. L is this x displacement is changing with respect to time. So then once we will go to the differentiation dx upon dt. So displacement of this means sorry, derivative of this displacement is what? Dx upon dt. If x is the displacement, then dx upon dt is known as in physics, in plus 2 level physics we have studied. Dx upon dt is,
V.
sorry,
V.
yeah,
No?
yeah. If x is
B velocity.
velocity, that's what the velocity is here. Because x is varying with respect to time. So dx upon dt will be the velocity. So that is why this is known as motional EMF. This is known as motional EMF. So motional means when the conductor is in motion. Am I clear?
Yes, sir.
Yeah. So please remember this. This result at least you remember. This will be very helpful. Otherwise later on. So this is what BLV. This is what otherwise. So it is same that BLV will work whenever there is a motion. This is not needed. Then one important point for today which I have to explain, that is, oh, it has been repeated. The slides have been repeated while putting. So many problems are there, but more problems better if we go by the get questions, then that would be more helpful. So here I will not discuss these questions. Okay, I think it's not there, but okay. Here on using the whiteboard I can explain that. This is not a problem. This is, we have studied that E is equal to minus of d phi b upon dt, right?
Yes.
And then I told you that this E can be represented as over the closed path. See this one carefully because this is perhaps I missed it in the slide, but this is here and this is very, very important. E E dot dl is means E dot dl is equal to minus of d by dt. See this derivation, but I'm trying to derive minus d by dt surface integral of b dot ds. Yes or no? Tell me. If any doubt, you may ask me.
Mm.
Yes or no?
Yes, sir.
So they say this b can be a function of maybe the space, maybe some other quantity, but we are interested in derivation of only d by dt. Okay.
Mm.
So uh, first this one. So we can rewrite this one as this as I can take this differential sign inside, and what I'm trying to write is very, very important. Del means partial derivative. Why I'm writing this partial derivative? This, as I told you that this b is now here. Let me explain that this b may be a function of suppose coordinates x, y, z, and t, but differentiation is being done with respect to t only. Yes or no?
Mm. Yes, sir.
So that's why I can write this as a partial derivative of b with respect to t. So this equation, very, very important. This equation is the integral form of Faraday's law of electromagnetic induction. That this side is line integral minus of del b upon del t. This is the integral form of Faraday's law of EMI. And here, if you apply the Stokes theorem, what would be the differential form? Can you derive? Yes, of course you can. Tell me.
Mm. Mm. Yes, E is equal to
Yes.
del
Speak loudly a little bit.
means E is equal to
E is equal to, no, here you have to apply the Stokes theorem.
uh,
So by Stokes theorem, what I can write here?
it is equal to surface integral
E is equal to,
del uh, means line integral E dot dl equal to
mm,
surface integral
mm,
del cross E
mm,
ds.
ds. So, and this side also it is surface integral ds.
Surface integral
So
means
if you equate these
del
two,
cross E equal to B.
del cross E is equal to
B.
not b,
Del, dou B. Dou B by 2.
yeah, minus of not the b, minus of del b upon del t. Yes or no?
Okay.
Tell me.
Yes, sir.
Very, very important. This is the Faraday's law of EMI, and this is the Maxwell's equation. Maxwell's equation in time varying field. Try to understand. If you can remember, for the static field, del cross E was equal to, in a static field, when I assembled those four Maxwell's equations, then at that time del cross E was what?
0.
0. But see, here this is not a 0. And I told you, if you can remember, that in time varying field, this equation will get changed.
Hmm.
Did I say yes or no?
Yes, sir.
Yes. So for the time varying field, this is another equation. There is a Maxwell's equation. So, and this is nothing but the Faraday's law of EMI. It is saying that the curl of E, that is the space derivative of E, is the time differentiation of B. That is why it is a time varying field. So del cross E is minus of del B upon del T. This is a differential form, and here its corresponding integral form is there.
Okay.
Is it clear?
Yes, sir.
Any doubt?
No.
So, okay, so let me proceed. So we have covered this much. See, the Faraday's law has got a lot of application. Magnetic tape reader, phonograph cartridge, electric guitar, ground fault interrupters, alternators, generator, transformer. Already I gave you that one example transformer, electric motors. So a lot of examples have been uh, there is a lot of applications it is having, and this is what the last picture I told you. Let's see, this is the equation already we have studied. E dot ds is equal to q enclosed, b dot ds is 0, e dot ds is minus of d phi b by dt, or in this their differential form, del dot e is rho b upon epsilon, del dot b is 0, del cross e is minus of del b upon del t, and one equation is missing.
Okay.
Which one is that? That is del cross H is J. Yes or no?
Yes, sir.
Yeah, so this four Maxwell's equation. Okay. Then we will go to the concept of this displacement current, and then this will be finished, and then we will start the questions um, uh, for until what we have covered. We have seen how a changing magnetic field can induce a current. See this eddy current. This, let me give you the few idea about this. The what do you mean by the eddy current? Uh, See, in a conductor, whenever there is a current induced or there is general current, it is having a tendency to flow in the form of these circular loops. In a conductor, on an area of a conductor, listen carefully, on the area of a conductor, the current flows in a circulatory manner. Are you getting my point?
Mm.
So this circulatory manner, the current, they looks like the, I mean, suppose, have you ever observed that while, suppose you are means standing near a pond or a river, and if you throw a stone there, then some concentric circle waves can be seen. Have you observed?
Yeah. Yes, sir.
Yes. So just like those concentric circle waves, these currents in a conductor flow like this. And these currents are called as eddy current. The eddy meaning is the whirlpool or those concentric circles. So this current is called as the eddy current, right? And now see, when this eddy current is there, and by the concept we have covered that the current always give rise to the magnetic field. Yes or no?
Yes, sir.
So now one we are have means one field magnetic field which we have applied, and one magnetic field will be created by these eddy currents. Yes or no?
Yes.
So this eddy current will produce a magnetic field which will oppose the change in magnetic field. See the external change in magnetic field. This is having a lot of applications in day-to-day life. This opposes the any external change in the magnetic field. So now see, these eddy currents are having the pros and cons both. What is the meaning of the pros and cons both? That if the eddy current is very high, then very soon your the electronic device will get burn out, because this will more will be the eddy current, more will be the heat generated, and more will be the heat generated, it will burn out. Yes or no?
Yes, sir.
But you can also use it for the some applications. This eddy currents. You may check it on the Google. Already it is there. The working of a metal detector. It is based upon the principle of the eddy currents. Okay. Here also you see microphones, roller coaster brakes. So these eddy currents are having the few practical applications. Okay, this is what it is saying also, that heat is from the eddy current. So if you don't want energy loss, so you probably think that eddy currents are bad, but that is not actually the scenario. See, induction stove, there also an AC current in a coil in the stove top produces a changing magnetic field at the bottom of a metal pan. This changing magnetic field gives rise to a current in the bottom of the pan, and because the pan has a resistance, the current heats the pan. So this has been utilized. The induction uh, stove has been is being used in the houses, and the eddy current is the concept which is leading to the use of such induction stove.
mm.
That's clear.
Yes, sir.
Yeah, and more you may just for your knowledge, you may just Google out there. Much more details are there. And is the
Okay.
actually I want to discuss now this very very important topic, the last topic for this before we start the EM wave, displacement current and Maxwell's equation. This is what a very very important topic. Let us see what this is. See, Ampere circuital law we have studied. What was the Ampere circuital law?
Mm, means in an ambient uh,
No,
surface,
what was that law?
means I is equal to
Sorry.
in the I is equal to
Mhm.
uh, integral H dot dl.
Yeah, not S dot dl, B dot dl or H dot. Okay, yes, S dot dl. Sorry, yes, you are right. S dot dl. That is line integral of magnetic field intensity. Very right, very right. So using that, see the Maxwell when he tried to apply this law in a capacitor, and, and what is a capacitor?
Capacitor means it stores charge.
Yes. Okay. So see what he found, that this law was applicable to the outside the capacitor, but he was not satisfied while he was applying the law. Means see, if this is the plate of the capacitors which stores the charge, you are very right. One is the positively charged plate and the negative charged plate. So when he was trying to apply in this space between this, then this law was inconsistent. Why we are saying the in, and this is also known as this topic in the books or while delivering the lectures, this is also given as the topic as the inconsistency with the Ampere circuital law. What is this inconsistency? I will explain in some other way also, but first let me explain here. So this was carried forward by the Maxwell, and he said, okay, if the current I is means H dot dl is equal to I enclosed, then this should be validated everywhere. The logic was right that it should be validated everywhere. Yes or no?
Yes, sir.
So then he said that okay, if it is, it should be validated everywhere. Then whatever is the orientation of the plate, it should be there. Means that same law should be applicable. Yes or no?
Yes.
Are you getting the point, or you're saying only yes? Means in doubt, you may ask. I will go into a little bit more details. So just see what I'm trying to say. That the shape of the surface used for Ampere law should not matter. This is what actually this was his means inconsistency which he was looking. He said, okay, Amperian surface you are taking, but why you are going for a particular shape? So that is what his first observation was, that shape of the surface should not matter. Then he said, okay, if this is really true, then imagine a soup ball surface with the positive plate. As you can see, this is the soup ball surface with the positive plate resting near the bottom of the ball. Okay?
Mm.
Just a minute.
Okay.
Hello.
Yes, sir.
Yeah. So
Hello.
yeah. Am I audible?
Yes, sir.
Yeah. So imagine a soup ball surface with a positive plate resting near the bottom of the ball. So he
Hmm.
said, okay, I'm taking an Amperian surface like this. Fine. Then I'm applying the Ampere circuitry law. Here it is written ds, but actually it should be dl. This is
Hmm.
okay. So I am applying the Ampere circuitry law to the charging capacitor. So there is no current enclosed by this ball. So this would be zero. Okay.
Hmm.
Fine. Up
Hmm.
till here, it was satisfactory. But see where the problem arose. Where did it arise? Let me proceed. Then it will become more clear. It's very, very important, this displacement current. Then he said, okay, that B dot ds is equal to mu naught times IC, or H dot dl is equal to IC, that's same. What is the relation between H and B? We know that B is mu naught times H, so H will be beta by mu naught, so mu naught is multiplied this side. Yes.
Yes, sir.
Then he said, you hold it right, it, and then see, sorry, see it is here. See, hold it right there, Paul. You can have it both ways, which is that you want. Then, actually, if you change the orientation here, then if you just tilt it, then you found that okay, there is a current. Then in that case, he is saying that okay, B dot dl is mu naught times IC. But in the previous case, you are getting B dot dl is 0. Means all it was depending upon the choice of Amperian surface. So this was the inconsistency, that choice of the shape of the Amperian surface was deciding the entire field. It is this much. Are you able to take this much?
Yeah.
Yes.
Yes, sir.
So this was the inconsistency. He said that no, there is something inconsistent here, and he worked it out that this should be validated. This inconsistency was removed by introducing the concept of displacement current. So he defined a term, displacement current, and see, that's very, very important. I will not go into much detail, but still I will explain at least the things which are needed. See here. Then he said that this B dot dl over the closed path is not only mu naught times IC, but rather for the time varying case, it is mu naught times IC plus ID. This was introduced by Maxwell, but he kept it for the ampere only, and this law is also known as modified ampere circuital law, or in some books or the somewhere it is known as Maxwell ampere law, because Maxwell did a contribution. Ampere was the, so Ampere gives up till here that we have already studied, and the Maxwell added this one. So this is known as the modified Ampere circuital law, or also known as the Maxwell Ampere law. Am I clear?
Yes, sir.
Now, what is this displacement current? This displacement current is known as, this displacement current is given as, if you see here, mu naught epsilon times d phi e upon dt. D phi e upon dt. This is what the, this is given as, means, or we also used to write like this also, epsilon times del d, or not epsilon, sorry, not epsilon, only del d upon del t, where d is the displacement current and d is given as epsilon times e. And this perhaps we have studied, epsilon times e, yes or no?
Yes, sir.
Yes. So d is given as epsilon times e. So just let me summarize the things, at least what we have studied, otherwise it will go in a different direction. Just a moment. What we are saying is that up till here it was okay, that line integral, you see, line integral b dot dl or h dot dl, it is same, just only mu will be multiplied. So this was the Ampere's statement. Up till here it is clear now? No issue?
Yes, sir.
I enclose. Then he said that this should be consistent. Then what he introduced that this is not only I enclose, rather this is mu naught times I enclose plus ID. Then he said what actually is ID? Then he said that ID is equal to displacement current is equal to epsilon times del E upon del T. Okay. Or if you take this epsilon inside, then this is nothing but del D upon del T. This is what I. So this is important. The displacement current is del D upon del T, where D is nothing but epsilon times E or epsilon naught for the general the air medium, epsilon times E. Are you getting the point?
Yes, sir.
And let me explain one more thing here. Inconsistency. What? See, what was the differential form of Ampere's circuitry law? Can you tell me?
Ambient circuitry law.
Differential form.
Del
Huh?
cross H
Mhm. Is equal to
equal
J.
to J.
So see, let me explain you the inconsistency by this angle also. Del cross H is J. If you take the divergence on both sides, so this side, what I will write? Divergence on both sides, right? This we will write.
Yes, sir.
And
Yes.
what? And I have told you that divergence of curl is always
0.
0. So it means del dot J is 0. Yes or no?
Hmm. Yes.
But we know that I have explained you del dot J is equal to minus of del rho v upon del t. This is known as equation of continuity. Yes or no?
Yes, sir.
So means at one time you are saying del dot J is 0. At another time you are saying del dot J is minus of del rho v upon del t. Means this is applicable only when rho v can be 0.
Yes.
So this was the inconsistency that this law is valid only when rho v is 0 means for the charge free reason. Rho v is 0 means this is for the charge free reason. Yes or no?
Yes, sir.
Yes. So then he said that no, this is not the correct form here. Rather, this should be del cross H is equal to J, that is the JC that was already there, that is the conduction current density, plus JD, that is the displacement current density. So this is the point form of modified Ampere circuitral law or Maxwell Ampere equation. JC plus JD, where JD already I have explained, that is epsilon times del E upon del T. Got the point?
Yes, sir.
So this is the inconsistency. So now we have completed the Maxwell's equation. So now there are four Maxwell's equations. And what are they? For the time varying field, there are four Maxwell's equations. And what are they?
Uh, del cross E equal to
Hmm.
minus dou B by dou T.
Hmm.
Mm, del cross H equal to
Hmm.
JC plus JD.
Hmm. Yeah. Tell me. What Maxwell's equation? So see, first is
Current
the
varying field.
huh, very simple. The first one is the Gauss law in first one is the Gauss law in electrostatics. So so what is that? So that is, if I ask you before proceeding, the Gauss law in electrostatics.
Del
Hmm.
del dot D equal to rho V.
Del dot D is equal to rho V, and uh, D dot ds is equal to rho V dV. Yes or no?
Mm. Yes, sir.
Yeah, here. Better this slide very easily we can. Del dot D is equal to rho V. This is for a static, but for time varying there will be change. This is a differential form. For time varying, del cross E, and this will become minus of, you see this slide very carefully. This will become minus of del V upon del T, and there will be a, as here it is in Gauss law, here we will write Faraday's law of EMI. Yes or no?
Yes, sir.
Del cross E is equal to J plus del D upon del T, or you can write JD. JD means displacement current. Del D plus del T, J plus del D by del T. Yes or no? And then this
Yes,
law
sir.
will be known as modified Ampere circuital law, or you can also say the Maxwell Ampere law. Yes or no?
Yes, sir.
And del dot B is zero. This is always zero. Yes or no?
Yes.
Yes. So these are the four Maxwell's equations for the time varying field. From here, you can easily remember, or you can easily derive the static for the static field, because for a static means what would be the del upon del t. For a static means if it is not varying with time, then del upon del t is equal to differentiation with respect to time is equal to, if it if it is not varying with time, then its differentiation with respect to time will be
Zero.
zero. So just you eliminate that term and you,
Zero.
and yes. So just you eliminate that term and you will reach to the here. Got the point?
Yes, sir. Yes, sir.
So STD is the special case. But the general, they are the four Maxwell's equation. And what are they? Gauss law in electrostats, Gauss law in magnetostats, Faraday's law of EMI, and modified Ampere circuital law. Am I clear?
Yes, sir.
It's very, very important. Very, very important, because from here only EM waves will be understood. So integral form d dot ds is q. No change will be here. What change will be here? Good see.
Um,
Or
means that will be minus
minus
surface integral
surface integral. Very good.
dou B
Yeah,
by
yeah, very good.
dou TD.
Del v upon del t ds. Yes or no?
Yes,
Yes.
sir.
And what change will be here? J ds plus surface integral j d ds. Yes or no?
Yes, sir.
Yes. And the fourth one will remain same. So this you should know. So today I will stop here. Tomorrow I will let you know the time. Tomorrow I will go for the class with the problems. That's very, very important. In the meanwhile, you, if you possible, you go through the revision of the theory. Problems we will discuss in the 1 or 2 class. Then I will proceed with the EM wave propagation. If you understand this much, then other things will become very easy. If you are messed up with these things, then other things will become very, very complex. Am I clear?
Yes, yes, sir.
Yes. So how it is going till now? Means how you are feeling about this subject now? We have covered.
Yes,
Means
sir, it's good. But the problem is I'm not getting time to study this.
no, you have to.
I'm
We will have to study,
time
because
is
see, already
problem.
we have got very less time. In between also
Okay.
we missed the very much classes because some commitments were from your side. sometimes from my side also, some festive occasion, it will happen. I'm not saying, but thing is that very less time frame is there. So then only it will be helpful if you devote some time. I understand you are having a job, a full-time job. So of course, you are previously also I said that still you are doing a very hard work. That after coming from your office, you are attending the classes, whatever days or time. So that is very very means really appreciating. But thing is that if you really want the output of this time, you will have to give your own time because my job is only to this much that I can guide you for the concept, theory, problem, but ultimately you will have to uh, get the things done by your own. Okay. Yeah. Yeah. If anything else you are expecting that you may let me know. I will try to give the more input. So if anything you may suggest, I can try it. That's not a problem. So if any such you may, please.
Fine.
Okay, so tomorrow we will be ready for the class. Okay, and that will be for the questions.
Okay.
So I will try to solve the maximum questions. If it is finished tomorrow, then okay. Otherwise, day after tomorrow. Because I don't want to leave any means doubt before we proceed to EM wave propagation. Because see, now the upcoming topic, especially the polarization. If you see the get, they are asking one question definitely from the polarization and EM wave propagation, and then transmission line, and then waveguide. So still some works are done. So first let me complete EM wave. That is very very important. How the wave propagate, what is the pointing vector, how to decide the direction. Then only I can say that yes, we have covered more than 60-70% syllabus. And questions are very very important. The more you will solve, more you will get. Okay?
Okay, sir.
Okay, so have a good time. For today it's fine.